so we're going to talk about this kinetics lab. I don't know why. The kinetics labs really are kind of my favorites. The equilibrium labs can be kind of fun too. So honestly, this semester, I think you might like better because it's more, it's just newer. So, I mean, that can be a double-edged sword, definitely. But there's just more interesting stuff, I feel like, that we talk about this semester. So we're going to find out the rate law for the reaction of thiosulfate with hydrochloric acid, okay? So before we do that, though, we're basically going to do, and is there, let me look at the lab, see how much intro we've got here that's not on the, where did I put it? There we go. Okay, so all of this intro stuff is basically just talking about the rate law. Where we really pick up here is where it says designing the experiment. Okay, so that's kind of where we are on the lab, because that's the part where it gives you the lab data, and then it gives you some pre-lab questions about the lab data that should help you to figure out exactly what you need to do when you're writing the procedure for this lab. Okay, so we've got this experiment, and in this experiment, sulfur is produced. Okay, now do you guys remember what color sulfur is? Solid sulfur by itself? It's yellow, right? Yeah, there you go. It's yellow, right? So sulfur is yellow and it smells really bad. I'll have to show you sulfur on Monday, if we didn't know that. Yeah, it's the rotten egg smell. Yep. Have you ever been to Yellowstone? Yellowstone? Yeah, there's a lot of sulfur in Yellowstone. That's why it kind of smells bad. All right. So basically what's happening in the course of this reaction is you're going from a colorless, or actually I guess in this one, the bromine's not going to be exactly colorless, but you're going from a certain color solution to a yellow solution, okay? And so what's happening here is you're putting a plus underneath the test tube, basically. And I don't know why they say a piece of filter paper. I think we're going to do this just on regular paper, probably, or that's what I would recommend, because otherwise you're just wasting filter paper, you know. All you're doing, basically, is you're putting the test tube directly over the piece of filter paper, or regular paper, and you're going to look kind of down on it as the reaction occurs, down into the test tube, which I wouldn't normally recommend, but nothing's going to spatter up at you on this one, and you'll be wearing goggles. And as the reaction occurs, as the sulfur starts to form, it starts to get yellower and yellower until eventually you can't see the plus sign anymore, okay? So we're cheating a little bit here because it's very difficult to measure the concentration, the changing concentration in a reaction. So this is kind of our tricky way of getting to the same point every time, okay? And so what we're doing is basically just measuring the amount of time to produce enough sulfur that you can't see the plus mark anymore when you're looking down through the test tube at the plus, okay? Does that make sense, the explanation there? Okay. So that's kind of what, what's happening. So it takes 40.1 seconds with those concentrations, all right? Then we're going to do a second trial, and this time we're using a different amount because we're diluting the Br2 just a little bit, right? Because before we used 5 mils of the Br2 and 5 mils of the MS. Now we're using 5 mils still of the MS, but now we're cutting the concentration of the Br2 basically in half, okay, because we're diluting it with water. So that's going to help us figure out the reaction rate, right? So cut that in half. Now the time for the reaction takes 79.2 seconds, okay? And then in the third trial, we do the exact same thing to the MS, right? So we half the amount of MS, which is, you know, you dilute it, that's going to half the concentration. And then you use the original amount of the Br2, okay? So now we have basically designed an experiment where we've measured what happens to the rate when we double the concentration of one of the reactants, and then what happens to the reaction rate when we double the other concentration, okay? So then we can tell what the, the order of the reaction is going to be for both of the reactants, and then we can write a rate law. Does that make sense? So we're basically doing experimentally what you have been analyzing on data tables for this unit, okay? So In the following above procedure, we would have different initial concentrations of MS and BR2 in the 3 trials. Determine these initial concentrations and enter them into the table below. Well, looks like that's been done already. So you have a table down below pre-lab problem number 7, right? Now, is everybody okay with why the concentrations are the way that they are here? So, experiment 1, it's asking us for the concentration, right? 0.05. Okay. Why is it that the concentration is 0.05? Because it lists the concentration here as 0.1. Well, it doesn't have as much to do with the 5 milliliters necessarily. I mean, it's sort of related to that. What are we doing here when we're doing the chemical reaction? We're pouring the two together, right? So you've got 5 milliliters of 0.1 molar Br2. There's no Br2 in the other container, right? So you dump these two together. Now the volume's 10, but we still have the same amount of moles of the Br2, right? So that cuts the concentration in half. Does that make sense? Because we're doubling the volume, essentially. So that's why, even though it says 0.1 over here, what you would need to put in the chart is 0.05 for those initial concentrations for that first trial, okay? For the second trial, the MS concentration is going to be the same, okay? But the Br2 concentration, we've already cut that in half by diluting it with water, and then it's getting cut in half again when it gets added to the MS. So then you end up with 0.025 as your concentration. And then same thing on experiment 3, you end up with 0.025 for the MS concentration and then 0.05 for the Br2. All right? And then we've also put in, or actually I guess this is already in here, the times that it took for each of those reactions to occur. Okay? What we want is not a time, though, because a time is not the same thing as a rate. Now, it would be, if you were just looking at the time, it would be easy to get confused here. Okay? Because the ones that take more time actually have a slower rate, right? Okay, those are the reactions that are happening slower. So if we take the inverse of the time, that will get things more like our brain is used to seeing them from this unit so far. We take 1 over the 40.1, and then the bigger times will give us the smaller numbers, the smaller rates. Okay? Yeah, I don't know. I mean, it's kind of cheating a little bit. I mean, you could do it with the time, right? But the only reason we're putting in the 1 over time instead is just so that it maybe makes a little more sense to our brains that, I mean, which reaction's happening at the fastest rate here? Yeah, see, I mean, you can probably see that. But just in case you can't, right, some people might say, oh, the 80.4, that's the biggest number, right? So just so that you don't get confused there, you take 1 over each of those, and then, I don't know. Yeah. So, you know, you may like that, you may not, but that's what they're asking you to do here when you do the calculation. I'm not real crazy about this method of finding the rate because the units it gives you are 1 over seconds, right? Which is not the units we're used to for a rate. Usually it's molarity over time, right? But again, it's just, you know, how do you measure the concentration of something over time? It's difficult, you know, unless you have good equipment. Now, the best way that we actually have to do it is using a spectrophotometer in a reaction where there's a color change that occurs, okay? Because then you can measure the absorbance over time, and you can use Beer's law. You guys remember Beer's law? A equals, am I doing this right? Where does the epsilon go? Is it little a? Stands for epsilon? Maybe that's right. I don't know why I forgot that equation all of a sudden. That, in the book, I don't remember what chapter it's in. Lowercase a? Okay. That's weird. I don't know why that stands for epsilon. But anyway, this is Beer's law, right? So if you know the absorbance, you can graph the absorbance over time, and you can figure out the concentration. Okay. So that's a good way to do it, which is why I want to show that to you on the second day that we do this lab. But for the first day, just do 1 over time, and that'll give you a relative rate, and you can work with that. Okay. So we determined the initial concentration. That's not really even a pre-lab question yet. The first pre-lab problem is, it says experimental design ensured that the reactant's initial concentrations were known at the instant the reaction began. Nevertheless, a key property was measured while the reaction was in progress. What was the property? So what was it that we were measuring while the reaction was in progress? Kind of the concentration of what? Of the sulfur, right? Okay, that's kind of what we were measuring in that one. Oh, never mind. I take it back. I guess we can't say we were measuring that necessarily because it's qualitative. We're using that, but we're measuring the time, okay? So we're going to use the time to change it into rate, essentially. Okay, so then what determined the amount of time that was measured in each trial? Here we go. This is what you were trying to answer. The amount of time measured in each trial was determined by, sort of by the concentration of the sulfur, right? Okay. In other words, the time required to reach the point where you can't see that plus mark anymore. So the concentration of the sulfur gets so great you can't see through to the plus sign. Okay? And hopefully we can be fairly consistent with that. A suggestion might be to have the same person making this measurement each time because, just depending on the vision of the person who's doing it, one person may be able to see the plus sign longer than somebody else. So you want to stay as consistent as possible. This isn't the best way to do this, but it's an easy way, so we're going to use it. Or not. You're developing your own procedure, right? You get to pick this. Okay. Number 3, why was it important to measure time to the same point in the reaction? So why is that important? Yeah. And why do we want it to be the same for each trial? Yeah, we want to make sure we're getting to about the same concentration each time, right? Because we need to get to similar points in the reaction, otherwise we're not, we're not really comparing things well, okay? So we want to make sure the same amount of each product gets formed in each of the trials. I don't even understand the fourth question. Sorry. Oh, I should proofread these a little bit better before I... There was another lab like that, wasn't there, where they messed up a couple of things? What was the condition? Let's see. Yeah, same amount of sulfur was formed in each. So I guess what they were looking for there was, what was the product that we were really measuring here? Okay. Really bad way to ask that question. But you already knew this. I don't know that we even need pre-lab problem number 4. I suppose you can cross that one out if you want to. Honestly, it's gonna confuse me while you're grading, so don't.
What if I just put it not?
I'm okay with that. As long as it's there, then I'm okay with that. All right. Yeah, sure. Put that in. That's fine. Jones does not proofread the lab. All right. So pre-lab, I had to repeat it because... All right. So pre-lab problem number 5, the rate law is expressed in terms of initial reactant concentrations. What do you expect would happen if we increase the concentration of MS? We've kind of already seen the data, haven't we? So, but what would you think, if you're increasing the concentration of something, what do you think would happen to the rate? Yeah, it makes sense that the rate would increase, right? The reaction would happen faster. Okay, that just kind of makes sense. Oh gosh, I really don't like this question either. If the rate of the reaction increases as the time decreases. Yeah, I don't think that's even the way they meant to say that. Let's try this. If the rate of the reaction decreases as the time increases. I think that's a better way to ask that question. All right, so cross out if the rate of the reaction decreases as the time increases. Okay, so as our reaction continues, the rate goes down, the rate decreases. Then what's the relationship between rate and time? So in other words, in general, what can we say about the rate of a reaction as it proceeds? What's typically going to happen to the rate? It's going to slow down, right? Okay, and what's the reason for a reaction slowing down over time? Say that again. Okay, because the concentration of the reactants are decreasing, so they're just not hitting each other as often. They're not colliding as often. So then we get less of a reaction there, okay? So the rate is inversely proportional to the time. Again, that's not a well-written question. I don't know. I went to this AP training this summer, and people teaching it just seemed so smart. You know, I should just proofread things better. Yeah, I'm not. If that's what they were saying, then I like my question better then. We'll just go with my question. All right. So now here's where we actually do something a little bit worthwhile. Calculate the inverse of the time for each trial, and enter it into the table. Well, that's not the useful part, but I think you can probably figure this out. All right. So I'm just gonna give you the answers here. 1 over each of these numbers is going to give you a decimal, and then you've got something that we can kind of pretend is is rate. Okay, not exactly the rate; it's the relative rate. Okay, right, relative to each other. So what that means, that's what screwed me up as far as being able to use this for any of those other experiments that I wanted to use it for, because this is not a molarity per second rate here. This is not a typical concentration over time rate. So we can't use it, we can't plug it into any of the formulas, unfortunately, and solve for our rate constant or anything like that, which kind of screwed up what I wanted to do with it. But it'll work for our purposes here, okay? So there's your relative rates, right? And then what we want to do is find the rate law, okay? So here's where I think maybe the way that I explain this is a little bit easier than the way that they explain it in the book. And I would go with my method if I were you, because I just think it's easier. What you want to do is you want to find a couple of experiments here where the concentration of one of the reactants doubles and the other one stays the same. Okay, so on this one, looking at the MS, it goes from 0.025 to 0.050. I would look at experiment 3 and experiment 1 if I were you. Okay, because that's where the concentration doubles for the MS, but the BR concentration stays the same. Okay, so notice it goes from a relative rate of 0.0124 to 0.0249 when you double the concentration. Okay, so then what is the order of the reaction with respect to MS? It's first order, right? Because you double the concentration, you double the rate. So it's first order with respect to MS. So if we're writing out a rate law here, it always starts with rate equals K times something, okay? So it's just going to be K times MS to the first power, because it's a first order with respect to MS. And then if you look at the BR2, that one we'd probably want to look at experiment 2 and experiment 2 and experiment 1. Yeah, I almost said 3. So 1 and 2 is what we want to look at here. It goes from 0.025 to 0.050. And basically the exact same thing happens, right? It goes from 0.0126 to 0.0249. So you double the concentration, the rate doubles again. So this is also a first order. So there's your rate law. Okay? Should be pretty simple stuff. Now here's the tricky part. We need to propose a mechanism for this reaction. Okay? And this is the part that you may not have even gotten to yet in watching the videos and stuff like that. But a mechanism is basically just a step-by-step, how does this reaction occur?
Linda, contact
Okay?
the main office, please. Linda?
So here's what we have to do on this one. Let me go back. Okay, here's the overall reaction, right? MsBr2 yields MBr2 plus S. All right? Now, we just decided that the rate law for this, the rate equals K times Ms times Br2. Now, the rate law, if you have a good mechanism, then the slow step in your mechanism should match the rate law as far as the stoichiometry, okay? Well, it just so happens this rate law matches the stoichiometry in this overall reaction, right? So what you've got here is one molecule hitting another molecule and reacting. Now you could propose some different mechanisms for this, okay? But because this is the rate law for this reaction, it looks like maybe this is just a single step thing. It all happens at once, okay? Now let's see if they agree with me, because I actually haven't checked the answer key that they provided here. Before I start making a video, that really would be a good idea. Yeah, single step mechanism, Ms plus Br2, yep, is consistent with the rate expression, okay? Yes?
Alex Brownell, if you're in the building, please contact Mr. Schlater's office. Thank you.
Okay, you can safely assume that the mechanism in your lab is going to be quite a bit more difficult than that, okay? We got to have some fun with it, right? But, yeah, the basic idea is that I need you to get from the pre-lab is just when you're writing your mechanism, you need to pay attention to your rate law, okay? The rate law is going to determine what kind of mechanism you can write for this reaction, okay? And this one is tricky. I'll help you out with it a little bit once we get done with the lab, but it's kind of a fun little puzzle to see if you can work it out. So anyway, that's kind of the process here. Does that make sense? I mean, it's not too difficult, right? So basically you're designing an experiment that would, whoops, that's it. So you're designing an experiment here to determine the rate law for this reaction. Okay, now you may already be able to see, oh darn, this isn't one-to-one stoichiometry here, so probably it's not going to be quite that simple when we write the rate law for this one, or when we write the mechanism for this one. But just go ahead and write your procedure similar to what we just did in the pre-lab, and then we'll take a look at it on Monday, and you guys will be good to go. Oh, tell you what, okay. Sorry, I thought of a change that I want to make here, and I know this is going to be a pain for a few of you, especially the ones of you who are here, but I want to make sure everyone is actually writing their own procedure for this one. So I want you to actually write out your procedure on the sheet that I gave you to start out with. That's going to be your procedure draft, okay? Once I approve your procedure, then you can transfer it into your lab notebook. But that way I can check everyone's procedure on Monday, and I can see that everyone actually made their own instead of relying on one group member to make the procedure for everybody. Does that make sense? Okay. And the thing is, the people who need to hear this may not watch the video. That's the funny part. Oh well. So we'll see you guys on Monday then.